everyone, welcome to episode 15, which is on reaction mechanisms. Now remember, this is part of a long series. We started at episode 10, so if you haven't watched 10 through 14, please stop right now and go back and do so. All right, reaction mechanisms are awesome. I love these. These are like nerdy puzzles for nerds, I guess, and they're so much fun. If you have the information in the problem, you absolutely will be able to find this answer. So these are super fun. Usually students don't mind this too much, so I'm excited to teach this to you. Okay, so the first thing we're going to do is just start with a question. So what determines the rate at which people get off an airplane? Is it how fast they stand up, how fast they get out the door, or how fast they walk out of the jet bridge? And for those of you who don't fly as much as I do, the jet bridge is that thing that connects the airport to the plane. So you walk out the door over this jet bridge into the airport itself. Okay, so try it out. Hopefully you're able to come up with an answer, and all I needed you to do is look at these three steps. So which is the slowest step is really what I'm asking about. Like, what determines the rate at which people get off the airplane? What is the slowest step in this process? So is it how fast they stand up? No, people can stand up really quickly. Boom, just stood up, right? Like you can do that like that. That's not going to change the rate. If everybody stands up as soon as the plane lands, you're not going to get off the airplane faster, okay? Let's look at C, how fast they can walk up the jet bridge. So if everybody's walking up the jet bridge by themselves, like at a normal rate, it's not going to change the rate of people getting off the airplane if you start running down the jet bridge. So the faster you go on the jet bridge is not going to affect the overall rate, so it can't be C. Therefore, it has to be B. And the reason being is there's only one door, and all 200 some people have to get out one door. That is absolutely the rate determining step. People cannot get off that airplane until they walk out that door, and it takes people forever because they have to like gather their bag and gather their carry-on, and most people are like, oh, I'm so surprised I have to get off the airplane now, so it just takes forever. Anyway though, that is considered the rate determining step. Now, depending on what type of scientist you talk to, they may refer to it as a rate limiting step. Both of these are totally fine, but because I learned it with rate determining, that's the phrasing I'm going to use. But let's start at the top point here. So when a chemical reaction involves many steps, each step is called an elementary step or an elementary reaction. So let's say we have a mechanism, and that's the overall thing that this is called. The mechanism has three different steps. So we've got step 1, step 2, and step 3. When we add all three of these steps together, we get our overall reaction. You and I have been dealing with the overall reaction for the past 9 months. That's all we've been talking about. We haven't looked at all at these elementary steps or these small steps that happen in order to take us from point A to point B. So whenever we have a mechanism, which is a multi-step process, every single one of those little steps is called an elementary step or an elementary reaction. Now, the rate of the overall reaction is determined by the slowest step in the elementary process. So out of reaction 1, 2, and 3, we're going to look at that and figure out which one was the slowest step. The slowest step, like our last example, was actually walking out the door of the airplane. And so because that was our slowest step, we would refer to that as our rate determining step. If we can figure out a way to maybe add like 6 or 7 more doors to the airplane, that would speed up our overall rate, and it would actually affect how quickly people can get off the airplane. Now, like I said before, all of the elementary steps together are called a reaction mechanism. Now, rate laws for chemical reactions cannot be reliably predicted from the overall equation. We know this. We talked about this in episode 11. If you remember, we had all of that data. It was the initial rates process where we looked at all that data, quantified it, and were able to determine a rate law. But just like we did with data, we have to do the same thing for mechanisms. You cannot look at an overall chemical equation and come up with a rate law. It's not going to work. Instead, what we do is we look at the slowest elementary step within the mechanism for the overall reaction, and then we can come up with a rate law. Okay, let's look at an example. So the first thing we're going to do is look at the reaction of 2A plus B2 and go to 2AB. So this is a two-step mechanism. The first elementary step has B2 going to 2B. So B2 going to 2B. This is a slow process, which shouldn't be that surprising because our B2 molecule splits in half. That bond actually breaks. And so we have to put energy in, break that bond to get 2 B atoms by themselves. Well, now as soon as the B atoms are by themselves, they see other A atoms floating around in the beaker. B reacts with A, and that's how we form AB. So we have a 2-step process that allows us to do the overall reaction here. B2 split apart to 2B, and then our 2Bs react with 2A to get 2AB. Now, our rate determining step is going to be this one right here. It's our slowest step in the overall process. So if we can find a way to break that bond more quickly, then we can actually get B2 and 2A to 2AB at a faster rate. So now there's a couple different things I need to point out here. In this mechanism, B is an intermediate. So molecule B, atom B, however we want to call this, B is an intermediate. So an intermediate is something that is produced first. Okay, so number 1, it's a product first, and then it goes on to be a reactant. So an intermediate is always going to be a product first, and then it's going to be a reactant second. So we can see it was formed and then immediately used up. For that reason, it's going to be canceled out when we add everything together, when we add our elementary steps together to get our overall reaction mechanism. Our intermediates are never, ever, ever going to be in our overall reaction. They are also not in rate laws, okay? Never, ever, ever are our intermediates going to be in a rate law. So if I came up with a rate law here and put B in there, you can automatically mark your answer incorrect because B is an intermediate. Now let's look at something else. Instead of an intermediate, we also have things called catalysts. My favorite, my specialty, things I love. So let's say we wanted to speed this reaction up by giving it an alternate pathway. So instead of B2 splitting in half to form 2B atoms, now what we're going to do is change the mechanism, change the way we go from B2 to 2AB. Okay, so let me get rid of that really quickly. So now what we have here is we have our 2C, which we said was our catalyst. So our 2C is going to be a reactant first, number 1. Catalysts are reactants first. Spelled that wrong close enough, okay? Reactants first. And then in the second step, they are going to be, because they're used up in the first step, and in the second step, they're going to be a product. So the reactants first, and number 2, products second. So if you recall, from the last slide we saw intermediates were the opposite. They were produced first and then used up. I never touch an intermediate, ever. It doesn't happen. I touch catalysts all the time. And so I physically grab my catalyst and throw it into my beaker to allow for that reaction to occur. So catalysts are reactants first, products second. Now the big thing here is, as you can see with what we did with the intermediates, when we add both of our elementary steps together to get our overall reaction, our 2 C's cancel out, and we see that our catalysts are not in the overall reaction. They are also not in the rate law. So catalysts and intermediates are often grouped together because they behave in similar ways. They are reactants and products. They're both used up and generated, and we have to make sure that they are not in the rate law and they're not in the overall reaction mechanism. Now, rate laws can include only, and I don't even like that, cross off can. Rate laws include only the species that you can control the concentration of. So they have to be reactants and catalysts, okay? Honestly, though, you are never going to put a catalyst in a rate law. That is super, super weird. Sometimes you can do it in Gen Chem because mathematically that's how it works. But in real life, you don't do it. That is a weird thing to do. You get laughed right out of your conference. Don't do it, okay? Now, number 2. Intermediates can never appear in rate laws because you cannot control their concentration directly. Okay, you can't do it. It's not going to happen. Now, number 3, this is the one I want you to kind of like think about and put in the back of your mind because we're going to come to it up in a couple examples here. But number 3, if there is an intermediate in the slow step, so something that is a product first, then a reactant. So if there's an intermediate in your slow step, you must find a way to swap out the reactants that led to the production of that intermediate. And I'm going to show you what that means in a little bit. But just keep in the back of your mind, intermediates can't be in your rate law. All right, so let's go through a couple examples here. Let's look at our first one that we've been doing here. If we assume that step 1 is a slow step, but faster than it was before because we put a catalyst in there, what is the rate law for this reaction? So how I would expect you to solve this problem is you go straight to find the slow step. That's the most important thing. Everything after the slow step, even if this was a 6-step thing, you can go over and just cross out. It is not important at all. You will never, ever use it. Anything after the slow step, not going to be used. So now you start with your slow step. and you're going to look at your reactants only. Okay, you only care about these two species. So you would come over here and write rate is equal to K, rate constant, times B2, and then you would multiply it times the concentration of C. Now, just like we've done before, we are going to use those coefficients and put them up here. Because technically what you're doing is you have B2 times C, so we just mathematically put them together and have C squared. Now, you should have a red flag in your head just screaming, like, that's not right, that's not right. And I'm like, yes, I'm so proud of you, great students, that's correct. Why is that not right? It's because you cannot put a catalyst in your rate law. So immediately cross that out and end up with rate is equal to K times B2. That's what your rate law actually looks like. All right, now your turn. Okay, I'm going to make it a little bit more complicated for you. I've given you a 3-step mechanism. Your first step is fast. It is in equilibrium because we're forming so much D, and our reaction afterwards is not actually plowing forward ahead because it's so slow. So that actually forces this reaction to be in equilibrium so B can move backwards to A and B. That's an important factor here. And so yeah, that's just important. That's all I'm going to say, okay? So take a second here, see if you can come up with your rate law. Good luck. Did you get it? Hopefully you did, but if not, do not worry about it. We are going to work through this together. Okay, so the first thing you do is you find your slow step. That's the most important thing, and you cross off everything afterwards because it's just going to mess with you. So you're going to start with your slow step here. So we've got rate, where do I want to write this? We'll go here. Rate is equal to K times your concentration of D times your concentration of B. So now, what you're going to do after you have your rate law is you go through and do like a little bit of a sanity check. And you need to make sure that each of your concentrations in your rate law were actually reactants. So the first thing I see is D. So I see D was a reactant here. However, it was formed in the previous step. So it was a product first, then a reactant. That is definitely an intermediate, so I have to eliminate that. So I'm going to put an X below it. I'll show you why in a second, but just put an X below. Now I'm going to look at B. Is B a reactant? B was definitely a reactant here, but you have to look at the first step. Was it produced first? No, it was not. It was actually a reactant, so B is good. We can keep B there. So what we're going to do now is look at this first step here and see if we can come up with an expression for D so we can substitute it into that rate law. So I'm going to come over here on the other side. So now I have rate is equal to, I'm not going to go there. I don't have enough space, so don't do that, okay? Come down here. We're going to go rate is equal to K1, okay? So K1 times A times B. Now, because that's in equilibrium, I can set that equal to the opposite direction, so the reverse reaction. So this becomes K negative 1 times D. So now I'm trying to solve for D or isolate D, so this becomes D, concentration, is equal to K1 divided by K negative 1, which we're just going to shorten to K. It's just a rate constant. These are all numbers. We would factor these together, times A times B. Okay, so now what we do is we come back to this original equation over here, and we substitute this in for D. So this now becomes rate is equal to K, which we're just going to assume includes K1 and K negative 1, okay? So now we put everything in from D, so that's A times B, and now we have to remember to bring our B down from before. Okay, so all I did was take this expression right here, where I substituted K1, K negative 1 for K, times A times B, put that right here, and then I added the B term from previously. So our rate law becomes rate is equal to K times A times B squared. Now, because this is the very first line or our first elementary step, you know A and B are both reactants and not intermediates, but it is a really good habit to look at that every time, go back, confirm, reactant, you're good to go. So the answer for this question is rate is equal to K times A times B squared. That's what I was looking for. All right, let's try another one that's slightly more challenging, but you can do it. You're brilliant students, no problem. All right, now here. Now we have 3-step mechanism, but this time our slowest step is the last step. So it's just going to be a little bit more arithmetic than when we just went through, but you can do it. All right, how'd it go? Hopefully you did a good job and you were able to figure this out. So what we're going to do here, like before, is you always start with your slow step. Unfortunately, here it's our very last step, which means we're going to have the most math to do in this entire thing, but that's okay. We can do it. All right, so you start with your slow step. So we've got rate is equal to K times F. So we're going to look here. F was definitely a reactant in this elementary step. That's a good thing. Unfortunately, it was formed beforehand. So it was a product first, then a reactant. That's the definition of an intermediate, so we cannot use F in our rate law. So instead, we're going to come here to our second expression and see if we can come up with a term for F. So I will go over here. Hopefully I have enough space here. Rate is equal to K2, second elementary step. That's why we're using subscript 2, times B times C, which is equal to K negative 2. Remember, it's a fast step that happens before a slow step, so it forces that to be in equilibrium. So now we can look at the reverse rate. So we have K negative 2 times F. So we can simplify this. I'm just going to use the rate constant K because we're going to end up doing that anyway. So B times C is equal to F. All right, so now this, the whole expression, K times B times C, is coming in right here. We're substituting for that F term. So this now becomes rate is equal to K. I'm just going to call it K. This is actually K times K2 divided by K negative 2 times F, which is B times C. B times C. Okay, so now we've got to go through here and check to see if anything is an intermediate. So we look at B. B was definitely a reactant here, definitely a reactant here. B is only a reactant. We can keep it. That's good. Now we have to look at C. Definitely a reactant here. Unfortunately, it came from a product. So it started as a product, then became a reactant. Classic intermediate. We cannot use it in our rate law. So now again, we have to do one more of these where we have to look at our first line, our first elementary step, to determine what our concentration of C is and see if we can substitute in two reactants that we physically touched in lab, that we touched and poured it into our beaker. If we didn't touch it, it can't be in our rate law. Okay, so now this one becomes rate, where will I write this here? Rate is equal to K1 times A times B is equal to K negative 1 times C. So sorry guys, I know this is a little packed, but we can handle this here. Okay, there we go. So now what we're going to do is isolate for C. So our concentration of C is going to be equal to K1 divided by K negative 1 times A times B. Okay, so all of this, AB, is going to be substituting for C. Again, we're just going to throw this rate constant into our rate constant here, K. So our new and official rate constant, rate law, is going to be equal to K times B. We can keep that, so I'm just rewriting it here. I haven't done anything to it. But now I'm going to substitute my value for C, which is A times B. You will notice B and B, so we have to rewrite this. Rate is equal to our rate constant times A times B squared. Okay? So hopefully this makes sense. If you have a slow step, then you have to work backwards all the way up until your rate law only contains things you physically touched in lab, which means they have to be a reactant. They cannot be an intermediate, and they really should not be a catalyst either. Okay? All right, last thing, let me give you a quick summary of what we just talked about. Number one, mechanisms can be unimolecular, bimolecular, etc. So unimolecular, one reactant. Bimolecular, two reactants. Trimolecular, three reactants. Simple as that. The rate of change depends on the concentration. If your concentration increases, usually your rate is going to increase. The only thing that doesn't happen for is zero order. Good. Okay, so now number two. Rate laws can be derived from data or from elementary steps in a mechanism. Data is what we did in episode 11. That was when we had those initial rates. Elementary steps is what we just did. I worked out two of those problems for you. So you have to use your elementary steps in order to derive the rate law. Now, we can use the method of initial rates to propose mechanisms. Our rate law from the method of initial rates should match the rate law derived from the slow step in the mechanism. So what the heck does that mean, right? So what this is saying is if I gave you a table of data like we did in episode 11, and I gave you a set of elementary steps like we did in this episode, episode 15, you should be able to come up with the exact same rate law for each method, right? For data or for the mechanism. The rate law has to be identical. Has to be. The data and the theory have to match. That's what that says. Last thing. The overall rate law needs to support the proposed mechanism. So you cannot have a rate law that has like reactants in there that you didn't even touch in lab, meaning you can't have some like random arbitrary chemical you never even touched or threw in. You can't have that in there. And so this is just saying that's what that really is trying to say is you must have academic integrity. You can't pretend that you put an elephant, a flamingo, in a beaker and then a barracuda showed up. Like that's not how that works, right? You have to have reactant A plus reactant B is going to react to form C. So we have to keep this in context of what we know we put in there in lab. That's all I got for you guys. I hope you liked it. I love mechanisms. They're like little puzzles. So go ahead and try a couple on your learning exercise. Have a great week. Take care of yourself and drink water.